Good afternoon, my dear teachers and friends. My name is Xi Chen. I'm from Peking University. I'm Professor Zheng Su's doctoral student, and I will graduate next year. And Zheng Su has many teachings this semester, so he asked me to give this talk on behalf of all of the authors. His work is collaborated with my classmate Yu Wu and with Professor Fazli Hussein from University of Houston. My title is a Lie group mean field theory for temperature channel and pipe flow. In 1904, Pronto presented boundary layer concept. This argument leads to the Blasius solution for the nominal boundary layer. However, the tabular boundary layer solution does not exist. Today, we combine the boundary layer concept with the Lie group analysis, and phenomenologically, we obtain an accurate analytical solution for tabular channel and pipe flow. So let's take a look at the mean velocity profile in the channel and pipe flow. Actually, there are two theoretical challenges. The first is that can we derive a complete mean velocity profile from the balance equation? The second is the common constant universal in the different wall boundary flows? This figure is from the Physics of Fluids in 2010, and it shows that the common constant is different. That's because they use a different fitting domain. Another question, meanwhile we can see that the viscous sublayer,
Do you believe in the third digit?
No, I don't believe that.
So how can you say that they're different? 0.384, 0.389?
Because in this paper, he gave a list of all of the reported kappa, and it varies from 0.36 to 0.45. So here is just give a explanation. Yeah. So indeed, in the textbook, Pope said that there are 4 layers in the tabular channel and pipe flows. There are viscous sublayer and above layer in the inner region, and there are load region and the weak region for the outflow. This coordinate is the distance from wall normalized with the wall units. Now let's take a look at the previous attempt to give the modeling for the MVP. It's the mean velocity profile. The first example is given by Nichols in 2004 in GFM. He proposed a 3-layer model, but it is no connection to the balance equation. The functions in this formula are just arbitrary. The second example is given by Monkowitz. It is a purely empirical fitting with the pedal approximates, and there are more than 15 parameters in his formula. So in 2008, Professor Itama, Lovov, and Rodenko, they developed a universal model for the tabular channel and pipe flows. They use a length function to model the effects of fluctuations. It means the Reynolds stress. And they also use a wall function and a wake function to obtain the entire mean velocity profile. However, the common constant are still different. There are 2% difference in these flows. So our work is just extends the LPR assumptions by establishing a framework of multi-layer symmetry analysis for length functions, and we found that can be used in a wide class of flows. So the mixedness is our choice length function. It is proposed by Pronto in 1920s and followed by von Kammer in 1930s. Now we can start from the integration of the mean momentum equation. This is the viscous shear, this is the Reynolds stress, and this is the total stress. It is driven by the constant pressure gradient, so it is linear away from the wall. Use the wall units, we can normalize this equation, and we introduce the function is mixedness. If we know the profile of mixedness, then we can substitute it into the equation and solve out the mean shear. So that's our basic logic. So these are the data. The DNS data is from Iwamoto, is from Himlice, and is from Wu and Moy. So it gives the profile of mixedness in log plot. So we can see that there are 4 layers in this profile. This is the sublayer, and this is the buffer, and we call this is the bulk region because there are in this region, the turbulent dissipation and balance with the production. And this is the core region because near the center of the pipe, near the center and the center of the channel. So the black line is the linear scaling first proposed by Pronto and von Karman. Okay, let's see the structure layer by layer. At first, we can see that the power law solution near the wall is in the viscous sublayer. The scaling exponent is 3/2. This can be explained by the Taylor expansions. So this is triple. And in the buff layer, we find that from y+10 to y+ about 40, there is still another power law solution, and the exponent is 2. Right now, we don't have an answer why this exponent is 2, but we guess it is related to coherent vortex structures. So when there is polymers or compressed effects, the scaling exponent will change. But we find that such power law still exists. So let's take a look at the out region. In the core layer, there is also power law solutions. This is the center and this is the wall, and the exponent is -1/2. This can also be explained from the Taylor expansions. So it is also a trivial result. But from this plot, we can see that the coefficient is different in the two flows. That's because the geometry effects is overviews in near the center of the flow. So the last layer structure is the bulk flow structure. We find that this is from empirical observation. We find that the structure is 1 minus R⁴ in channel and 1 minus R⁵ in pipe flow. This plateau supports the existence of such structure. Now we ask a question. So what's the relation between these structures with our balance equation? Now our answer in one word is they must be a set of multilinear Lie group similarity solutions. Must be, I learned from Yuri, because he said as a single guy learned, we must say there must be. Okay. We explain this sentence by the following 3 steps. The first step is that we can search for the symmetry transformation for the balance equation. This is the balance equation in the out region. Nothing is neglected. It's the full non-viscous equation with the Reynolds average. The dot indicates the derivative according to the coordinate. R is the distance from the center. So the symmetry transformation of this equation can be solved by soft wall, and however under the boundary condition, nearly all of the symmetry transform are broken, but the dilation transform is permitted by this equation. So the epsilon is the Lie group parameter. It indicates how much you dilate, and alpha is a parameter. It indicates that in which the direction you dilated. So this is our symmetry transformation. So using symmetry transformation, we can solve out the invariant surface. The invariant surface is a function of the Lie group invariance. The invariance is a first integration of these characteristical equations. The logical is that the meaning is that they just use as we solve for the streamline equation or the stream surface equation in the fluid dynamics. So here, the invariant surface is it's solved to which the function in this form keeps invariant when dilation group is performing. It's just give such meaning. So the last step is that now we give our similarity solution for the balance equation. So there are 2 possible local similarity solutions. The first one is F1 equals to constant and F2 equals constant, and it will lead to the power law solution as we have observed. Now the second is that when the power law is broken, F1 is not equal to constant, but F2 still equals constant. Then it will lead to our bulk flow structure. So these two specific solutions describe the empirical solutions as we shown in the previous figure. So what we want to say more is that common constant is also a Lie group invariant in the bulk flow. This is demonstrated as here. From this general solution, we let the boundary condition, and we will solve as Lm equals to this formula. And this formula generally asymptotic to the linear scaling level, so it gives a definition for the common constant. Something new is that since this equation is unclosed, we can postulate a form for the F1 and F2. Then we solve out the G2 and G3. So in this case, this equation can be satisfied. The question is that the postulated form between F1 and F2, can they be verified by the empirical data? So we have a new transition ansatz. This ansatz is our assumption for the F1 and F2, and these parameters are constant in the bulk flow and in the core flow. So from this transition ansatz, we can solve out the solution. Is describe the mixedness from the bulk layer to the core layer. So then we use the multiplicative rule. Then we can obtain the mixedness profile for the entire outlet. So this procedure also can be applied for the inner regions. So this plot shows the composite solution, scaling solution from the viscous sublayer to the buffer layer, and the blue line shows the transition from buffer layer to the log region. And here's a figure. As in the figure, the plot indicates the transition ansatz, because there we introduce the free parameter. So the value is 8. Then this value is the free parameter here. So now we can we give a summary of all of the solutions in each layer. So these are the local scaling solutions that we in the previous figure, and these are the composite solutions using the transition ansatz. So then we use the multiplicative rule layer by layer between the two adjacent layers. Then we can obtain the entire solution for the mixedness. So that's why that's our final result for the mixedness. And from this formula, we can solve out the mean shear, solve out the velocity profile, solve the average velocity, and the friction factor. But there are still some free parameters. With the Y sublayer thickness, viscous sublayer thickness, and the buffer layer thickness, and the core layer thickness. And I will take a little bit of time to show how we measure this parameter and run figure. Okay, this figure shows the measurement for the common coefficient. It turns out the common coefficient equals to 0.45. It's 9/20. And each plot has been vertically shifted. And the Reynolds number carrying nearly 3 decades, from 615 to 100,000, to about 100,000. The method is actually the least square use the measured velocity with our theoretical function. This is our theoretical function. So the previous plot is here. The above figure has been vertically shifted, and this plot shows that they are collapsed into one single line. The slope is 0.45, and the UD is the defect velocity. This is the center line velocity. So, and the domain, actually the domain is for y plus about 200 to the center of the pipe, to the center of the channel. So it indicates that the common constant is bulk flow property. And we have also measured for the core layer thickness is equals to 0.27 in channel flow, and nearly about 2/3 in pipe flow. For the sublayer thickness and the buffer layer thickness, we can do some asymptotical calculation. Then we use the empirical data to determine its value. It's about 10 for the Y sub and 44 0.5 for the Y buffer. So now we can show the result for the pipe flow. This is our result for the pipe flow. So now we can share some results with you. The first, we compare the predict mean velocity profile with the empirical data. Each profile has been vertically shaped. This is channel flow, and this is the experimental data. And here shows the relative error. The red colors are our model, and the error domain is within 5%. Nearly all of the main points, the error are within 1%. And Fourier's number covering over nearly 3 decades. So it demonstrates that our model is very accurate.
What is this PRL 2008? What do you mean with that?
This?
Yeah,
the blue
paper.
This
Paper by okay.
Yeah, I'll call check. Yeah. Okay, we also have the prediction for the center line velocity and the average velocity. And from this result, we can find that the center line velocity between the difference between center line velocity and the average velocity in pipe flow is 4.26. And this prediction has been verified by the experimental data, and it's much accurate than the Pope's result. Yes, for the center line velocity, our prediction is that the same real number, the difference is 1.1. This is also this is the first time to give such prediction, and it is verified by the empirical data. So for the engineering interest, we give a new relation between the friction real number and the bulk real number. This is the old formula. It's from the Pope's textbook, and this is our new formula. And the blue line is our model, and the red line is the original model. So this is the compensated plot. For the tendency is saturated. It means that for the even higher real number, our model is accurate. Okay. So the last prediction is for the friction coefficient. The dark line is the Pranto's formula, and the the red line are our model. And through the composite plot, we can see that there is a transition for a real number at about 5,000. The one indicates the Pranto's formula. So we explain that this transition is due to the increasing of the core layer thickness. It's from the 0.27 saturated to 2 sets. So we give conclusion. So we present a multi-layer boundary layer theory for the MVP. We have found the similarity solution for the distance layer by layer, and then the constants are measured but not weighted, and then this framework can be extended to other mean-field quantities such as kinetic energy and to other flows, for example, rough fiber, compressible channel, and the TBLX. So this is the example we show the model for the kinetic energy. So we introduce a new length function in analogy to the mixed length. So and we also give a multi-layer description for this length. Then we can have the entire profile for the streamwise kinetic energy. And another extension is for the TBL. This is the mixed length in TBL, and the multi-layer structure is the same. And the core layer structure, we even do not need the core layer structure, because that layer goes to the free stream. So with that, the velocity difference is variation is within 1%. So we did not need the core layer structure. So for this structure, we can give a very accurate description for the universal profile. So thank you very much.
Are there questions?
Gentlemen.
I didn't quite catch how many parameters you have in the thing. Can you explain once more how many parameters you have?
How many parameters?
The exponents, for example, I mean, how do you determine 1/8, 1/4? Is this a parameter?
Okay. This parameter has the
3/2, 1/8, minus quarter, all these are parameters, or? You are determined theoretically.
For the scaling exponent, we observe from the empirical data.
So it's fitted.
Yes.
So it could be not 1/8, maybe 0.126.
The 8 is made in this figure because you can see in this figure. So this is a plot. It's measurement for the this parameter.
So it could be 1.126, for example, instead of 0.125.
If the DNS data shows that it's equals to 145, then we use 1.5.
No, 0.126 instead of 0.125. Can you distinguish? No. So this is another parameter then, this exponent. So you have some 16 parameters.
I have three kinds of
No, you have also the exponents. The exponents are fitted. So there are parameters. All these exponents in this function are not determined theoretically.
Yeah,
They are fitted to the data.
Yes.
So there are 3 parameters that are fitted. So I'm asking how many of these you have. It seems a lot.
How can I say that? Because the scaling, there are 3 kinds of parameters in this formula. The first is the scaling power. The scaling power, the first scaling.
So 1, 2, 3, 4. The R to the 5, the Y sub, the Y buff, the R core. All these are 3 parameters, right? I count 1.
Y is 4. We put it on Y is 4. The scaling is minus 1/2, and this can be explained from Taylor expansion. And this sharp is 4 can be explained by the central symmetry argument. We can do some expansion for the mixing length. Then we use the parabolic assumption for the center. Then we'll solve out this parameter equals to 4. But for this parameter, the scaling is 2. I have explained that we didn't have answer yet. And for this transition sharp is 8. We just use data to show that how this come from. Yeah. This is.
Are there other questions? If not, we can thank all the speakers.